So what do we mean with the chemical and petrochemical industry in this case? So takes ourselves, first we have sort of industry, and we will hear later about steel and cement. And the last one of this sort of big three is chemicals. And in the chemical industry, then we have a major part is the petrochemical industry. So everything using oil and petrol products, natural gas, to produce chemical products is in there. So a large part of this is polymers, so plastics and everything like that. Another important part is fertilizers and ammonia, which we will hear about also in a moment. But then there's a whole range of other kind of products in this sector. So rubber, specialty chemicals, etc. And placing this in terms of emissions, the industry, excluding energy, has 26 of EU emissions, and of this, the chemical sector has 12%. But that is only talking about the direct emissions from this sector. You can also see it in a different way and talk about the final energy. So then the chemical sector uses even more of the industry total. But even that doesn't tell the full story of the petrochemical industry, because the final energy doesn't include all the energy that you put into the products. And I tried to find a value for how much of the total energy, how much of the emissions it accounts for when you include this, and I couldn't find anything. And that's one of the things that makes this sector extra difficult to decarbonize. So chemical industry, and then in our meta-analysis, they all look at different parts to some extent of this industry. And usually, since you can't look at everything, the focus often lands something like this. Polymers, that's often the main focus. And then sometimes also fertilizers are included, and the rest is a little bit more, not as detailed. So that is also what I will sort of discuss when I move on. Talk about the meta-analysis. So in this project, we looked at many documents, 17 documents, and we chose to look at only the scenarios that reach net zero emissions in their given scope. And our focus was also on the Antwerp, Rhine, Ruhr, Rotterdam area. So we selected mainly those from Germany, Netherlands, and Belgium. But then to get a little bit more perspective and a little bit more, we also had some on a European level and some global. And that's the first title page of the report, and it is out if you want to read it, both in German and English. We took a rather broad approach and investigated a range of aspects. So first of all, of course, what are the total emissions, total production volumes, and energy use in the reference year and in the final year. And then I want to see, so of all the strategies you can use to reduce emissions, what is sort of the most important? Can you answer that? And then in the future, if you're not going to use fossil feedstocks and fossil energy, what sources are you going to use instead in these roadmaps? Then, since these are roadmaps, something happens with time. So what happens to emissions and the technologies that you're going to use? When do you assume these will come into play? And also, qualitatively to capture sort of the discussion in these roadmaps, or also some of the main challenges, opportunities, and policy recommendations mentioned. So that is also what I will present now. And I'll start with the sort of shape of emission reduction. So here are some of the roadmaps where you can see this, and as you can see, they are all kind of around the same area. Some are a bit more linear and some are a bit more slow emission reduction at first and then more rapid towards the end to reach net zero. And probably the earlier emission reduction has more to do with switching out the energy, while switching out the feedstock comes a bit later. So how do they achieve these emission reductions in the different roadmaps? And for that, I have this rather complex image, so I'll take you through it. Maybe you recognize it from earlier today, the poster, where we have different roadmaps with different scenarios. And then in the columns, we have first the emission reductions that they achieve in this scenario. And then we have a range of different strategies to use. So the first three is recycling biomass and CCU with hydrogen. Those then mainly relate to the feedstock and changing the feedstock. Then a lot has to do with the electricity. So we have electrification and reduction through the electricity emission factor. And then some roadmaps also switch energy to other kinds of renewable energy like biomass. And of course, reductions through CCS and efficiency improvements, which is usually energy efficiency improvements. And then other for what didn't fit. And then if you didn't use any of these strategies, what is kind of the increase that they would see then is what this sort of growth factor captures. So a darker color means a higher value, so you don't need to see the tiny little values on the screen. You can just see sort of where it's dark, that's where it's the most important. And then you have those yellow where it says NQ, it means that this strategy in this scenario is important, it's a part, but they haven't quantified its contribution like this. So what does this really tell us? This is rather an overview, so not to look too much into detail, but it tells us that there is rather a range for the petrochemical industry to reduce its emissions, and it has to be because it's different kind of emissions. But it also tells us that it's not really clear what the relative importance is of different strategies. It's really, in some scenarios, one strategy is really important, and in another it's completely different. So it's unclear what will have the most impact. And I should also say, I told you already, you can't really see the values, but you also shouldn't look at it too carefully because all of these have different scopes and different methodologies. So compare them like this is a little bit tricky, but it still gives an overview. Yeah, then moving on to the feedstock composition, there's a range of roadmaps shown. If you don't use fossil, then you use recycled feedstock, chemically or mechanically recycled, or you use biomass, or you use synthetic feedstock based on captured CO2 in some way with hydrogen. And most of these scenarios then show a mix of these three options, rather than sort of switching all to one. And that's also natural because all of these have limitations, like how much renewable, how much waste material you can find, and how much sustainable biomass there is available, and how much, at what price, and how much electricity you need to produce synthetic feedstock, and if you can even find them, technology development, etc. So all have limitations, and it's kind of natural that there's some kind of mix. But we also see again, it's not really clear which is the most important. That's still to be seen. I can also note that in this case, sometimes, since this roadmap sometimes only look at the chemical sector as such, it doesn't look at recycling because that's part of the waste management sector. That's why it's sometimes not quantified in this way, even though in some cases it's a really important part of the future feedstock in these cases. A quick look at where the energy will come from. is a bit more clear for once. It's about electricity, it's about electrification, and this, I think, doesn't include electricity needed for hydrogen production and for feedstock. So if you include that as well, it's a whole lot more about electricity. Now, which are the technologies that are available, and when will all these new things come into play according to these different scenario analysis? I will not go through each line here, but we try to get a sense of this by grouping the different technologies that they mention and when they mention that they come into play. So each sort of diamond here means that one roadmap says this technology will come into play at around this time. We have different kinds of chemical recycling, we have bio-based routes, we have CCS and CCU technologies, and then other new processes like electric steam cracking and methanol to olefins. So there's quite a range of different technologies that are important for this transition. And again, when they come into play, it is around this period to 2025 and 2035, but within that range, it's kind of, again, varied. Some are a bit more centralized. For example, chemical recycling is put a little bit more 2030, but for a very important technology, methanol to olefins, it really ranges in this sort of assessment. So, and there's quite a big difference if it comes into play within 2 years or 12 years. So, again, a big uncertainty here. And regarding the qualitative aspects and the discussion and the roadmaps, here at least, it is things that we've heard before, and they kind of speak the same language here. So I'll just quickly go through this because I think we recognize these things. There are huge challenges and huge costs. Making these options available, creating a business case, it's not there, it's also expensive. The infrastructure is not there. And then a few also still mention the opportunities about becoming a leader of climate action, green growth opportunities, business opportunities, and some also mention some synergies, for example, grid balancing. Since the chemical industry will use or produce hydrogen and use electricity or hydrogen, it can kind of maybe function as some kind of balancing, but sometimes mentioned. And the recommendations, we also recognize a bit, it's about providing this business case. Some of the roadmaps mention a bit more specific tools like carbon contracts for difference, different ways of cheaper electricity and creating demand through green markets. And then not a lot about reducing the certainty and uncertainty, economic uncertainty, so risk sharing, infrastructure planning, and strategies for new resources like biomass or CO2 or whatever. And then, of course, as in all cases, adopting the policy framework where it's not really aligned with what this kind of completely different shape of industry needs. But again, this is something that we recognize from before, so I think it's known to us. So that was the sort of results, really in short. The takeaways then, first of all, I have already kind of highlighted that there is, for this sector, still a lot of uncertainty and a lot of unsure things. And naturally, it's a complete transformation of an industry. Of course, there are uncertainties, but some factors are especially important, like the resource availability of the different kinds of feedstocks, for example, and of course the electricity, as always, and the price. It really matters which strategy is worth going for. And then technology development and timing, how will the technologies work and when will they be available? And for this sector, especially the scopes that they use in these roadmap analysis really matters. So what emissions do you include and what sinks do you include? It makes a difference for how you view this system when you make a roadmap. And here there is no really like, this is how you should do it, because what scope you choose depends on kind of the questions you want answered. But in any case, you have to restrict it, but I think you should always keep the overall system in mind in any case, so you don't sort of forget what happens just outside. And the scope is also important for how you talk about the energy, like do you include the electricity needed for hydrogen production or not? So matters. And then it's a tricky thing about policy, because when you make these roadmaps, it's most policies are pretty difficult to model when you can't put a number on it. But it's still an important part of the narratives and discussion of these roadmaps. It's something to really pay attention to and have a big impact on the transition, how it will happen. But at the same time, the big variations makes it really difficult. Looking at this as a policymaker, trying to imagine what will happen. I mean, I get a little bit confused. I bet they get confused too. So it's still very important to be able to present it in a way that makes sense. So we still want to be able to kind of see into the future and get ready for the future. So it's so important to make scenarios, and we will do that also in a later part of the Greenfield project. But what to keep in mind then, I think, is that since all different strategies have limitations or are problematic in some way or another, we should still allow sort of all kinds of strategies and focus on reasonable combinations to stay within sort of sustainable boundaries as much as possible. Also considering that the previous results are already very varied, and it's partly unavoidable since the future is uncertain. So we still need this kind of differentiation, but to show a clear message and to show what we need to do right now, there's a need to focus on the more plausible and robust short to mid-term pathways, so that we need where to start. But these sort of pathways should still include some kind of robustness towards different developments in the future, so avoiding lock-ins, for example, because it's about the decisions that we make today really decide which paths will even be available tomorrow. With that,
thank you very much, Ylva. Does it trigger questions among the audience or for the people online? If you're, hang on. If you're still with us, well, I bet you are. You're shy. Does it trigger questions? Oh, there's one chat box. Oh, another one is coming in. Fine.
Thank you for your presentation. You talk about risk sharing and risk analysis. So when you talk about risk analysis, are you thinking about risk regarding technologies, risk and their evolution and reaching a certain maturity, or are you talking about their implementation, or are you talking about the risk regarding CapEx, or what is the definition of risk in these evaluations? Thank you.
I think it's more or less all. Yeah. Yeah, I think it's a lot about the money and making these investments, and then the risk sort of is as an economic thing, as an economic factor between this. So I think that's the kind of risk that we usually talk about.
Thank you very much for your presentation. If I know this is a very general analysis overview, but if I would ask you on your assessment, having read all those informations and reports, what is the one or two trends that you think are more exciting for the next 5 years that you think that are under like 1 or 2 or 3?
And I'd say,
Trends generally, technological, raw materials, whatever.
I think for one, just that a lot of these roadmaps have turned up in the last few years. So I feel like there's a lot happening that in and of itself. And that you're sort of understanding, okay, well, what are really the technologies that are important, like methanol to olefins and chemical recycling, however. And then also, yeah, that. But it's so, since it's still sort of so all over the place, it still needs to settle a bit. And I feel like it is sort of maybe settling a bit in the discussions right now, but it's not quite there yet. So I'm still a little bit waiting, but excited to see what happens.
Ylva. I thought it was really interesting to see, and I heard you said something about that from this stage, you're going to develop scenarios for the chemical industry or economics. So, I mean, based on these results, where everything is sort of very much dependent on which kind of pathway you would decide upon, right? So sometimes biomass is huge, sometimes carbon capture and utilization, etc. Recycling, uploads. So when you build your scenarios, I think my question is kind of similar to yours, like, so which routes are you going to explore? Like, which are the ones that you will perform in the next work? Like, how do you build upon this asset?
I think what we are going for now is to sort of highlight a little bit more the potential of cycling more carbon within sort of the system. Because now it's sort of like more and more preference for capturing CO2 and combining with hydrogen, and then you import that from somewhere else. But that seems like it requires a lot of, it's far away, it requires a lot of electricity. There is still a value to be captured sort of within the industry and keeping the carbon in loop. So I think that will kind of be the focus of our scenarios this time around. I'm not sure yet. We will see sort of what the model tells us and how we will differentiate and where we find the interesting stuff.
I think it was a great presentation. It's usually a mess to put all this data together. So yeah, hard work probably. But my first question would be due to methodological issues. Usually, sometimes we have like the sector-specific roadmaps, and sometimes road mapping for a sector is being conducted for, I would say, an overall system analysis. So did you look only at the sector-specific roadmaps, or also like on the second one, yeah, how the chemical industry evolves in an overall system? And if yes, you also looked on the second one. Have you observed differences by tendency?
We have a sort of both. You can also see it sort of like I showed you, some don't include the waste management because they focus specifically on the chemical sector. Some of the roadmaps we have maybe only looks at sort of plastics, have a more life cycle approach, and then of course you're gonna involve this whole thing. And I think my approach was, since they're also different in so many different ways, I couldn't really decide, okay, these are the ones that I'm picking out. So it is kind of a bit of the variety is within that. But yeah, I can't really tell if I see a difference more than in how you then present sort of your emission reductions and what part of the life cycle that you focus on.
interesting because, you know, when you make an overall system analysis, for example, and you also model the energy supply, you know, and then you figure out, okay, I don't have, for example, enough renewable hydrogen to cover the demand in the chemical industry, then you might maybe then put a higher assumption for maybe recycling, you know. But I mean, you can see it more when you do an overall system modeling, but you can't see such things if you do only sector-specific modeling. That's why I'm asking. Maybe, yeah, let's see. I will have a look on the report. And the second question would be, do you see like which I mean, we have seen, okay, it's quite heterogeneous. So there are different technology development pathways described in each of the roadmaps. But is there like a common sense with regard to policy? So my policy designer question, okay, all the routes and scenarios might be different, but is there one policy solution which fits for all? You know, and does it make it different from policy perspective?
So your first question again, I think those that have the sort of chemical industry sector, they are usually in a bigger paper where you include the other sectors as well. So you do get this kind of holistic perspective there as well. Policy one size fits all. I don't know, but I think it's the same as for most sectors, you know, about electricity and yeah.
Cheap electricity is
Yeah, I think that is what you will always kind of hear. Yeah, but it's sort of these issues here and there, like there was an issue about trade with CO2 or trade with plastic. That is these kind of issues that can be a bit more specific that just kind of need to fix the screws.
Different needs sometimes, different pathways as well.
Yeah.
We're just going to take one last question and then we'll move on to the next one.
Or actually, I think creating demand and green lead markets is maybe one of those that really comes up a lot. Yeah.
Rather a remark than a question, but based on what you just discussed, there is a general understanding perhaps that just like what we have had in buildings, we've had in machinery, we've had in even equipment that we use at home, we have energy labeling of different equipments. Can we imagine in future, because really to compare different plants and different let's say processes, to have energy labels of some sort in the future and to be driven by policy, because without which we are comparing so many, we have so many scenarios, we are comparing so many things which are not so easy to compare. Would it make sense to have that kind of a policy framework where we are able to label and give labeling and we can buy those kind of things? So I know, for example, in the steel industry, we have responsible steel, which is one way of doing it, perhaps, but it is not the most complete way. I don't know what is happening in other sectors. And if there is some kind of a meta labeling or meta kind of a system which can allow you to have category A kind of plants, category B kind of plants in terms of energy, not talking about CO2 yet, but in terms of energy.
So also not about labeling of the products, but of the plants themselves.
Just like homes,
Mhm.
like buildings we have today, building that A, B, C, D, E. Mostly in Europe, everywhere we have that.
I think one other thing too, it's a lot about creating the demand so that the facilities that want to transition know that they can sell their products when they're done. And apart from sort of green lead markets, it's some also mentioned this kind of labeling of sort of green products. But I haven't heard this about sort of that for the industry complex itself.
Sorry, Ali.
Yeah.
What was sorry?
Maybe just to add on your question, because you mentioned this. Maybe just to add on your question, because you mentioned responsible steel. I mean, there is an activity on EU Commission sides ongoing which is a sustainable products initiative. Yeah, it doesn't limits to plants, so it's more a product approach, but with a life cycle analysis. And that's the question: how to analyze, so to further develop the eco-design directive to not only analyze energy-related impacts, but as well the whole lifetime impact, and then you also have the production in there. I mean, and I think chemicals are also to be assessed maybe in future, but steel is also a topic, I think, right now. Yeah.
Thank you very much for your questions. I guess we'll just get on from there. Thanks a lot, everyone. And I don't have the sugar or the thank you for I'll tell you one later. Thanks. So now we're going to have a second presentation on the ammonia industry, another important one. This one will be conducted from my dear colleague Antoine from ADEME, and we're going to talk a little bit about food. And someone is saying thanks. All the presentations coming up well online. We'll just assume it does. Antoine, the floor is yours.
Thank you, Elliot, and hello everyone, and thank you, Elliot, for this invitation to this side event. So today I will talk about the transition pathways for ammonia decarbonization, and we are going to make a case study of the French situation because it's quite different on the other pathways that we can look at that were already made. So I would like to start with a question. So maybe we can pose the question for ourselves. So what is the purpose of an industry net zero pathway, in your opinion? And it's quite a difficult question, I think. So the pathway, in my opinion, is not to make a line between today and 2050, because the transition will not be linear. In my opinion, the purpose is not to do a curve, because there are many of curves, as we can see on the previous presentation. We can take a lot of different directions with different technologies, different solutions, like biomass, like CCS, like hydrogen. So in my opinion, the purpose of an industrial net zero pathway is to show the turning points. It means what are the necessary transformation of the chemical industry, and here the ammonia industry, during the following years, especially on 3 areas: the technological one, the change in the market, and the financial one. So there are already a lot of publication on the ammonia deep decarbonization. There are a lot of pathways that have been made globally on the global pathways with IEA, on the European pathway with IRENA and on DECEMA, for example. So it's really nice work, and I like to see these pathways and to study this report, because I'm quite passionate with ammonia deep decarbonization. But in France, and actually at national level, we don't have the same ammonia market together. We don't have the same industry. We don't have the same starting point. So we don't have the same energy resource and price. So actually, all these beautiful reports does not make any sense for our policymakers and our industrials. So they need to be transcribed. They need to be adapted to the specific case of at the national level, where the law are made, but the subsidies can be given. So we are doing a lot of pathways in ADEME in my company. So I'm working for the French Agency for Ecological Transition, and especially in the industrial department. So we are doing 2 kinds of pathways, actually. The systemic one, which is a big model with energy and resources, and we are trying to see what are the pathways to reach the net zero goals at the national level. So we made four pathways, which are really different in terms of vision of 2050. From S1, which is frugal generation, where maybe the level of consumption are very low, to S4, which is restoration gamble, and then the deep decarbonization is quite advanced with a lot of technology, with a lot of artificial intelligence. So there are very different vision of on 2050, so different pathways to reach this goal, to reach the net zero. Then we also made transition sectorial plans at the industry level, and this exercise allow us to see really deep into the main challenges of the industrial domain. So we focus on these three areas. The techno one, so it means what are the solution for energy efficiency, the CCUS, CCU, what are the costs, so how much CapEx it will be to implement these technologies. Also, we are asking ourselves what are the evolution of the market from the chemistry of the cement. So we are modeler. In the model, we can change the demand, we can change the consumption for maybe buildings, for transport, for anything you want. Then, after the study of these three areas, we can draw some summary, and we can try to implement like a public and private action plan of these pathways. So today I'm going to not to talk about the left side, but about the right side, the transitional sectoral plans of the ammonia. So just to show you how ammonia market is different compared to the rest of Europe and the rest of the world. So in France, the ammonia market is 1.7 million tons, and actually we are big imports of ammonia. We produce only half of our ammonia for fertilizer mostly, and also for the chemistry. It's very different compared to the rest of the world, where maybe 80% of the ammonia is used for fertilizer. In France, it's really different because we import a lot of fertilizer and we use ammonia for the chemistry sector. We also import a lot of our fertilizer. Yes, that's what I say. So the urea parts, we import actually all of it. The nitrogen solution and the ammonium nitrate is more produced in France. We have also a really specific fertilizer mix compared to the rest of the world. In the global scale, urea and nitrogen solution are used a lot for the fertilizer, whereas in France it's more ammonium nitrate which is used for the fertilizer purpose. So the ammonia French industry is also different of the rest of the Europe and the rest of the world. We have 4 sites, 2 in the Normandy, which is next to the sea, 1 on the south of Paris, quite in the middle of nowhere, and the last one next to the German border. They are very small to medium size sites, and the 4 represent 1.5 million ton capacity. In terms of energy consumption, it's 11 megawatts per ton of ammonia, which is 120% the best available technique. So we saw with this number that energy efficiency is still required and our production sites are not really optimized. In terms of emission, the emission is quite important also because it's 2 tons of CO2 per ton of ammonia, whereas the IETS benchmark is 1.62, so maybe 25% more. And the ammonia production represents 3% of the industrial completed emission in France. So just before talking about pathways, I would like to remind you maybe the free decarbonization challenge of the production of ammonia. So the production of ammonia is based on steam methane reforming. So you have natural gas and air and water as a raw material, and natural gas also as an energy provider. And the steam methane reformer is here to produce hydrogen. Then hydrogen is transformed into ammonia through the Haber-Bosch processes. And the ammonia is again transformed into nitric acid, urea, or ammonium nitrate. Here you can see the GHG emission, which are heavily located on the steam methane reformer, but also on the ammonia transformation into nitric acid because of the nitrous oxide emissions. Like every chemical processes, they are heavily integrated. It means that if you change something on the steam methane reformer, you have there is an equilibrium that will be break, or at least will change between all the processes and all the equipment, because there are a lot of heat which is exchanged all around the site. So yes, 91% of the emissions are concentrated on the production of hydrogen. These emissions are quite concentrated and already captured for the CO2, for the processed CO2. And here there are this heavily integrated heat exchange. So that's made the decarbonization of ammonia production site very difficult because of this equilibrium that will change. So actually, we have some few decarbonization levels, of course, energy efficiency, small electrification, and also the removal of nitrous oxide from the nitric acid production, but they are limited in terms of potential. So if we want to succeed a deep decarbonization of ammonia, we have actually two ways. First way is the hydrogen way, which requires a new process. So if you want to go to this way, actually you need to close the steam methane reformer and to replace the hydrogen with electrolyzer, and also the nitrogen, which was bring with the air. You need now air separation unit to feed the Haber-Bosch processes. Actually, this solution, you can implement it progressively until 10–15% of hydrogen, and then you have to change from 15% totally to the 100% of hydrogen, because the equilibrium is not good anymore. So you need to have a complete retrofit of your site, a complete electrification of your site, and it requires a lot of time and difficulties. With this way, you can avoid actually all the CO2 emission. The 90% emission stands for the 10% emission, which are remaining with the nitrous oxide, but not shrinkage. The other way is the CCS way. So actually, the process is still identical, but you need just to add a new capture equipment on the CO2 from the gas combustion. And also, like the H2 way, you can remove actually all the CO2 emission of this process. There is a bit of difficulties. It's the need of CO2 infrastructures, and likely it will not be everywhere on the territory. So if you remember the France and the 4 sites, maybe it's likely that 2 sites are eligible to CCS because they are in big industrial zone, whereas the 2 others are in small industrial zones. So it's not likely that there will be pipelines of CO2 in this area. So this solution actually can just be applied for 2 sites in France. Okay, so let's start on the pathways. So the transition is not just a story for engineer, I think. The transition needs a broader context. It needs it's not just an addition of technical solution and then we measure energy, we measure emission. I think that the transition needs to be seen as a broader transformation of the society. So we need to see what's going to happen in terms of markets, also with the technology. So in terms of markets, the parameters that are really important for the fertilizer and the ammonia industry is, of course, agriculture. So it will change the ammonia production if you have different agriculture models. So we made 3 scenarios with 3 different vision of the world in 2050. So from the left to the right, and in the middle, we have the reference one. So the reference is based on the trends of agriculture. It's based on the actual trends for the international exchange, and also on the stated policies and the decarbonization announcement with some extrapolation from industrial. On the left, we have the pathways, which is named resilience and renewable ammonia. So in these pathways, the agriculture is less intensive than today, is more focused on bioagriculture. There is also in this context transition a strong European autonomy and a need for autonomy, especially on fertilizer. There is also in this context a lot of electrification and the need of hydrogen infrastructure development. On the right, the pathway is named low carbon ammonia and globalization. So it's quite the opposite of the blue scenario, because in this one, the agriculture is more intensive than today, but also more precise. Maybe you can have some robots and some artificial intelligence which help you to maximize your yield or your agriculture. There is also a lot of globalization, so a lot of exchange of ammonia and fertilizer. And maybe that's in this scenario that the Europe is lacking of competitiveness because of the international exchange and the very expensive electricity and hydrogen. So this one are the result of the reference emission. So first you can see that the production there is a small decrease in production of ammonia because of a small decrease in fertilizer consumption. Then you have the 3 small levels of energy efficiency, electrification, and nitrous oxide removal, and then the 2 big levels. So in this scenario, we don't think that are going to have a complete retrofit of the ammonia production. So we are just maximizing the H2 integration until the 15%, and we are maximizing the CCS integration only on the CO2 process and only on the 2 sites which are eligible in France. And here we can see that with these stated policies, with this announcement, then we are not going to the right direction. We are not going to the net zero. The objective are not reached. There is an insufficient decarbonization in this scenario with the 66% compared to 2015. We can also see that there is actually a lock-in of emission after 2035 because industrial wants to choose, doesn't want to choose now between the H2 and the CCS. But H2 and CCS are completely exclusive in the 2050 world. We have to choose now, actually, if we want to go on the H2 way, on the CCS way, because the CCS way are just, because the H2 way is remove the CO2 from the CCS. So you as an industrial, you can't say today, oh, okay, I'm working on both solution H2 and CCS, and then we'll see later because then you want to rentabilize it. Yeah, you know, make it profitable, of course. And So it will lead to lock-in emission. So we here are the results of the blue scenario, the blue pathway. Then in this scenario, there are a decrease of imports. So actually a sort of increase of production around the 2030, especially because of the effect of CBAM and the strong Europe. Then you have the three levels, the energy efficiency, electrification, and then nitrous oxide removal. And we are going into H2 infrastructures until the retrofit is possible around 2040, 2045. So in this scenario, we retrofit the 4 steam methane reforming, and then the decarbonization is now complete after 2045. We can also see that there is actually a low decrease before 2040 because the technology is not ready yet. The infrastructure are not ready. Maybe the electricity is also a bit expensive until this time. So this scenario shows that we need a very strong hydrogen strategy, which is required to allow this path and allow the infrastructure and electrification to be made. We also can see that there is no need of CCS in this scenario. Then, and finally, the last scenario, the last pathway. So in this world, if you remember well, there is a lot of globalization. So actually, there is a lot of imports and the increase of imports in fertilizer in France. So the ammonia production will decrease. And it's a really high risk of offshoring in France if we are going in this way. We can see the three main small levels. And you can also see that the H2 is too expensive here to be implemented. So actually the only deep decarbonized solution is the CCS for the 2 steam methane reformer out of 4. So it's not a complete decarbonization. We just reached 81% compared to 2015. And we hope that the other chemical industry can do better than the ammonia industry in this scenario. Just an investment comparison between the last 2 scenarios. So we can see the difficulty of the good scenario versus the orange scenario. So it's like more than 3 times the capex investment, especially due to high cost of electrolyzer and the retrofit of the 4 sites. Okay, so I will finish my presentation with a summary for some decision maker. So this is an ongoing work, and we are now trying to have some discussion with decision maker, with industrials, and with ministries to know what to do for the ammonia production. So three principal messages. The decrease in fertilizer consumption can be offset by the reinforcement of the value chain. So that's what we saw in the blue scenario. Okay. 10 seconds. Perfect. So for that, just here, some ideas for agriculture. Maybe choose ammonium nitrates, which are more efficient and less emissive, and have also the advantage to be produced in France. So it's like good for agriculture and for our industry, rather than the imported nitrogen solution. And we also have to build some green certification label for this green ammonia, for this renewable ammonia, which is less expensive, which is more expensive, sorry. And also to compensate maybe the lack of fertilizer, we can transit the market from the fertilizer to the new renewable ammonia market. So from maritime transport, for example, or the H2 storage. In terms of infrastructure, we can see that in France, 2 sites require H2 integration. So it's actually a message for policymakers and industrial that they can begin to draw a strategy for these two sites, because in 2050 the deep decarbonization of these two sites are the H2 is necessary for these two sites. Then you have the two other on the sea, which can choose between H2 and CCS, but they have to choose, because we saw that if they try to do both at the same time, there will be lock-in emission for a long time because of the infrastructures. Then lastly, the mandatory public support, especially to help the transition, because hydrogen is very expensive, and we also need some infrastructure and electrification to go to the hydrogen way. So yeah, and also need to be supported for the transition with some mechanism like CFD or the European PEC, and also avoiding gas. Actually, there are some gas taxes that are not paid by industrial, so maybe re-equilibrate this energy prices differences between electricity, which is already expensive compared to gas. So re-equilibrate these two vectors. Okay, so thank you for listening.
Thank you very much for the presentation. I see there's only 1, 2, 3, 4. Chris, first.
I'm sorry, I hope I was paying close enough attention, but with the option, CCS option, was there any consideration of switching from SMR to autothermal reforming, so you had a much more concentrated gas and it's cheaper to do the CCS?
Yeah.
Okay.
Yeah, it could be possible. It was not seen here because of the industrial plants that are actually not taking this solution into account. So
okay.
Yeah, but it could be a solution too. Yes.
It'd be hard to retrofit to an old plant, but it was a big one. That's what I'm doing.
Hello, hi. Thanks for the presentation. There is a number that you presented that I just wanted to get my head around, maybe get a bit more clarification. You did presented the carbon footprint of ammonia at 2.0.
Yes.
2.0 tons of CO2 per ton of ammonia. My understanding is that the carbon footprint of hydrogen production alone via SMR is approximately 10 tons of CO2 per ton of hydrogen. So I think
that's like you need at least 5 times the weight of hydrogen to do a ton of ammonia. So that's why
what I'm trying to say is that the carbon footprint of ammonia that you've presented should be higher than the carbon footprint of hydrogen.
So hydrogen has a weight of 1, 2, and H3, and has a weight of 15.
But you have to produce hydrogen before you produce ammonia.
Yeah.
So
Thanks for that. I was just trying to put my head around having
maybe a short question, but also when the invitation, we did the same sort of analysis for the trilateral region, Belgium, Netherlands, and Germany. So we looked at the site of BASF in Belgium, chemical site in Germany, in the Netherlands, and Dortmund. So there's the same type of production processes taking place, same routes to go to net zero. What we figured out, of course, is if you work together in this region, that's the invitation. I think we should also work with the northern part of France together. You can definitely save on cost of pipelines, for instance. And
yeah, exactly.
if we do this on the different sites in an independent way, costs will become much higher to decarbonize and to keep the production where it is to be.
Yeah, so it's a thing that we can add to the summary for policymakers, of course. And also, that's also why we don't take the CCS solution where the sites are too alone, like in the middle of nowhere. Because the infrastructure are like too expensive.
Just so that people online don't feel left over, I'm just gonna take the question that's in the chat. Considering the energy stored in methane, which process is more efficient between getting H2 from SMR and from electrolysis?
I think it's the H2, but
Which process is more efficient?
yeah, maybe
H2.
there are some experts in H2 in this.
If someone in the outside. Well, we just, meantime,
For the both solution, we have quite far from the optimal theoretical energy conversion. So from methane reforming is like 5.8, I think, the theoretical, and we saw that in France it's 11 megawatt per ton. For the H2, I don't have the numbers in mind, but we also have some losses of conversion. So I don't know.
back to that, if someone has an answer. Ali, next.
Okay, and maybe one question, as you mentioned, electricity is still more expensive compared to gas in France. I'm not sure if it's after the war, but I think several years ago, methane pyrolysis was also like in the debate to produce at least carbon neutral hydrogen if you like find a solution what to do with the solid carbon. But what's with this solution? Is it not on the plate anymore, and why? I'm not sure. It's also referred to Ylva maybe because this sector is also relevant. I'm not seeing it anymore. Is it due to the war, or do you have some kind of explanation? Or maybe you? Sure.
That is why we also proves that if you look at natural gas prices today, or at least half year ago, it was completely out of the compared to even green hydrogen production. And you need to develop a market for the carbon, the cycle that produce that volumes that the market does not exist.
But the gas crisis was just in Europe, so actually the ammonia market was not really affected. So it was just the ammonia production sites, so in France and in Germany and in this country, which were closed for temporarily. So yeah, there is the increase in the crisis in the gas, but for the ammonia market, which is really easily transportable, that doesn't matter.
And one other question from Solar. I have also a question about biomass. So why do you use biomass? So
Yeah, it was of course
hydrogen.
yeah. For hydrogen, yeah, it's also a good solution, but we didn't consider it because of the competition for these resources. And the industry can decarbonize itself maybe easier than just take all the biomass from maybe the buildings or for the heating. And so yeah, it's a choice at the beginning of the project not to take biomass into account like the main level of decarbonization, and try to see the solution with only hydrogen and CCS. But yeah, it's a choice.
Negative emissions, because we have to extract the biogenic carbon out of the resource.
Yeah, yeah. After it's
carbon dioxide that becomes because of this, right?
yeah, it could be interesting. It will be an economical.
And then another question: did you consider for the electrolysis? Did you consider pressurized system, or is it just a conventional hydrogen at 1 bar? Because the price to pay in the hydrogen production is the compression.
Yes, I think that the electrolyzer already produced compressed hydrogen, maybe not as much as a hybrid wash processing, of course. So I think the pressure was 30 bar, and then you have to to put it like at 200, 250 bar for the Haber-Bosch process. So you need electricity and
I didn't consider those.
Yeah.
Thanks a lot for the questions and for the presentation. I think if there's no more questions, we can move on to the next one. Thank you very much, Antoine.
Thank you. And then I'd like to call to the bar, Chris. So I think there's no one better to talk about the steel industry. I'm gonna have a presentation on the steel industry. I hope the people online are still awake and that sound is still good.
Yeah, sure.
Perfect. Thank you, Alan. I can see the train is making you vibrate with the camera.
Okay, good, perfect. Everyone can hear me? Okay, so you're gonna see a horrifying number of slides go by here because this is part of a standard package I use for teaching all NGOs, finance community, what have you, right? So I'm gonna pick and choose what I have for this community, which is mainly engineers, and we won't stop too fast on this. Nope, not 2 hours. So how steel is made today, what parts of the process do the GHGs come from? And this is really important understanding how to target where the technologies are and how to target policy. Obviously why we need material GHG steel. So a year ago, it was 7 pathways. I'm pretty sure we're at 10 pathways now to decarbonize steel. Like technologies are coming out of the woodwork at various TRL levels. This is based on a study we did in 2021 leading up to COP27 called Net Zero Steel, which turns out to be version 1. We're doing Net Zero Steel 2 right now, and I'll explain what the differences are as we go along. And it's basically a series of geospatially details. We took basically someone else's database of all the steel facilities globally. We sorted out, what their wind and solar resources were, how much access they had to CCS, what have you, and then we tried to convert them to something. And one of the several technologies that most of you are aware about at this point in time. We'll go through some key global and country results from version 1. And some important details on how steel emissions are measured, because you're going to hear a lot of different funny numbers. And just some global policy implications. So not going to spend too much time here because I'm going to spend more, I'll go through this in some detail, but there are 4 main steps here for making steel. The raw material production, so if you're doing blast furnace steel, you need coal, metallurgical coal, which you make into coke, which you use to make carbon monoxide in the blast furnace, which is the actual reductant which pulls off oxygen. You get the sinter plant for iron ore. Today's blast furnaces are great for a reason, because they can use all sorts of varying qualities of iron ore, because they cook this iron ore as it comes up the belt heading into the blast furnaces, and they make little globules, and there's quite a bit of emissions there. DRI is much more, the technology you heard about, direct reduction, is much more specific about the type of iron ore it needs, and that may be its greatest weakness over the coming decade and a half, given the steel industry is used to taking in all sorts of varying grades of ore, and DRI requires a much narrower version. Then you need lime fluxes for slagging to take impurities out of the steel. We then move on to iron making, which is where most of the emissions are, and the 2 main technologies are blast furnaces and DRI furnaces, and I'll explain more about those in a moment. And then steel making. So basic oxygen furnace, 70% of the global stock today. Electric arc furnaces, 25, roughly, yeah, so 25 of it's DRI, 25 of it's recycled, 5 of it's DRI, and then we've got the electric furnace. And then you get structural forming here. Now, all these technologies tend to share the same structural forming processes, one way or the other, and this is mostly electrifiable one way or the other. It'd be expensive compared to using cast or coal, but it's readily electrifiable. So this is just the main thing for those of you who aren't aware of steel. 70% of steel in the top left-hand corner there. So you get coal made into coke, coke goes into the top of the blast furnace.
Iron ore gets sintered, goes into the top of the blast furnace. It enters as a solid, it's spun, it heads down. The coal catches fire, combusts, goes to carbon monoxide, provides heat, basically melts the iron, and then the monoxide strips the oxygen off the iron ore, and you end up with liquid iron at the bottom, and a whole lot of impurities, which is the slags, which come off or stripped off. And the liquid iron goes into these torpedo cars there, over to, it's called a converter here, also a basic oxygen furnace, and then to the refining stand where it's mixed with magnesium and nickel and all sorts of other things. The converter is what makes it from iron to steel. So the key distinction between iron and steel is that steel has somewhere between 0.1, 0.5 to 2% carbon in it, right? So really there's not a lot of carbon that's required to turn iron and steel, but just enough to give a rigidity to the material. At the refining stand, we also meet the secondary route where scrap comes in. It goes into an electric arc furnace. It's often preheated, melted, then goes to the refining stand. And the electric arc furnaces can make any quality of steel depending on the quality of the scrap that goes in, right? So if it's carefully sorted, all the copper is brought out, all the various contaminants, you can make pretty well anything. And the Americans, some American companies are doing something really interesting now where they're running high-tech mini mill arc furnaces. They're carefully sorting their scrap. They're adding just enough of what's the DRI briquetted iron in, and they're making basically almost any type of steel out of 80 to 90% recycled steel. Okay, so this is a bit of a model where China might go, you know, as the scrap content builds, where perhaps Europe might go in the future. We're just kind of used to this. The blast furnace, basic oxygen furnace route. It's a bit, you know, it uses really, it can use any quality of iron ore, and we know exactly what we're getting out of it. Yeah, don't want to spend too much time here. The top right is a map. If you want the details of this, just Google net zero steel. The technical report's all there, the data for all these diagrams. Most of the upshot here is that a large chunk of the world's steel fleet was built in China somewhere between 1995 and 2015. These are relatively recent, highly efficient furnaces. Okay, and they could be around well past 2050. After about 20 years, they get their first interior relining. After another 15 years, another relining, and after another 10 years, another relining. We want to catch these furnaces at their relining points because that's when they have to stop everything. It's quite expensive to rip all the brick out, and then that's your chance to rip out the blast furnace and put in a DRI unit or something else if it's available. Key thing here is really North American and European steel production does not matter from an emissions point of view. It's all Asian, okay? One way or another, it's Japan, South Korea, and especially China, which is 54% of global production right now. Seaborne trade, iron and steel raw materials. Basically, the Chinese are digging up Western Australia and moving it into China, turning it into infrastructure with a lot of iron ore also coming from Brazil. That's the two big thick arrows there. This sort of maps where the iron ore is today. The largest quantity of high quality ore remaining in the world in terms of reserves we know about are in Brazil. So if we want to do a lot of DRI, it's largely going to have to come from Brazil, probably. The Australians have magnetite deposits that they can upgrade. They're 33% concentrated. Magnetite is obviously, you can use electricity to concentrate it and magnets to concentrate it, but it would take quite a bit. You'd have to make a new mine, concentrate it up to 66%. And then there are smaller deposits around the world, South Africa being one, which is why I mentioned iron shipping of green iron earlier today. This is where the metallurgical coal, again, digging up Australia, moving it to Asia. Now, the interesting thing is BF-BOFs have been coming kind of at the end of their the end of their sort of efficient life. There were big improvements out through to the 1970s in terms, apparently about 100 years ago, we used 7 times the amount of coal for a given ton of steel that we do today. Like this, they were so inefficient. We've made these things so much more efficient, but they've stopped getting more efficient. Like we've kind of hit the thermodynamic limits. The only way to improve BF-BOS is you make them bigger and bigger and bigger. You run them in continuous casting so that the standard big units are about 5. The big ones today in South Korea, China, and now in India are 5 megaton units. Which in the late 1970s, when we were worried about energy efficiency to a much greater degree, or at least hope when we are now, led to the invention of the direct reduction technology. It's used for its multiple metals, and it operates at a much lower temperature. You pre-treat the iron ore into these little pellets. With the DRI reactor, you run a syngas of hydrogen and carbon monoxide through the reactor. The carbon monoxide provides heat to drive the reaction. The hydrogen takes away most of the oxygen. And with obviously the monoxide becoming dioxide. And what comes out of the bottom is a solid sponge iron. It's about 4 to 5% carbon. And then that goes into an electric arc furnace and you do your sliding there. Just going from the best available blast furnaces to DRI units, you cut emissions in half right there, boom, right? This also, if your syngas, if you construct your unit properly, the syngas, the carbon monoxide that comes out of the top of the reactor is relatively concentrated, and you can do CCS on this if you're careful about it. And there is a 60% capture plant in Abu Dhabi doing this today, and CO2 goes for enhanced oil recovery. A key thing about DRI reduction too is if you don't care about letting the iron cool and then reheating it later, you can get sponge iron, compress it into briquettes, put it on a boat, and send it anywhere in the world. So the steel making and the iron making parts of DRI making can be done in one place, say Brazil or South Africa. You make green iron, then you ship it to Europe, or you ship it to Europe or to China, and they just do electric arc furnace making to make the steel that they require potentially. And again, with the implication that you can get the hydrogen you need for I'll get into that in a moment. The syngas can be completely hydrogen. It's not syngas, then you can use completely hydrogen as your reductant if you have an external heating source for the reactor. And if you can do this in places where you can make clean hydrogen really cheaply, you can make very, very, very low emissions iron. Prior to the pandemic, this is kind of roughly what steel prices, the cost of making steel was. Commercial BF-BOF sort of in the 400 range with some uncertainty. DRI was a bit more. Scrap totally depends on the cost of scrap. Electricity to a little bit, but it's about the cost of getting good quality scrap. And generally, it's under the global price, but steel prices wing and wang all over the place, with China kind of structurally overproducing simply because that's the way they plan their steel making compared to their demand. So most of the emissions come from the reduction step. So there's iron ore preparation, there's iron making with some in steel making, and if you can get the reduction step, you knock out most of the potential emissions. Won't spend too much time here. We all know why net zero iron and steel is essential. I don't need to tell this group that. So how to eliminate reduction in smelting in steel? Okay, this again, there are 2 more technologies that are not in my latest version of this. First thing is less demand, more material efficiency. We don't really think about minimizing the use of steel in construction, one way or the other. We can cut it by about 20. Basically, architects and structural engineers, if they even think about it, can cut the use of steel by about 25% and stay within today's building codes. It's the same, effectively the same with cement and concrete. Come on. There we go. More recycling. Recycling is limited by the amount of scrap that's available and high quality scrap. If the scrap gets contaminated, especially with copper, all it's really good for is rebar. You need really low copper levels and selenium levels, I believe, in order to make really thin sheet steel. And again, you can add a little bit of extra new DRI briquettes to it to get below the contamination levels. And that's something that can be done today. And there's been a lot of discussion about blast furnaces with CCS. I think this is totally technically viable, but I really do think it would take a decade and about $5 to $10 billion to make this work. Simply because the flue gases are highly variant, these things turn on and off. It's not like trying to do CCS with gas, but I'm more than willing to have that debate. Another technology that this was the preferred option for decarbonizing steel before we taught in between BF-BOFs with CCS and HDRI. And the idea is you kind of eliminate a few steps. You just put coal in, you inject oxygen into the reactor. There was a lot of work done in Belgium, I believe, as part of the ULCOS project. Eventually, Tata walked away with the IP. It showed that it's quite possible to put, basically more efficient. It's steel that uses less energy, but it also produces a concentrated flow of CO2 coming out of it, right? Which makes it a lot cheaper and easier to do CCS. But again, Tata is sitting on Hysarna right now, and we don't know what's going on with that project unless somebody else in the room knows more than I do. Again, syngas-based DRIF, EAF, we talked about it, and replaceable with 100% hydrogen, which is what's going on in northern Sweden right now. And then the wild card is electrolysis, right? So there are several startups. Boston Metal keeps making a lot of noise. They come into the news, they go out of the news, they come into the news. And the most I can ascertain is they're somewhere around TRL 3 to 4. They are before the real deep gap where you start spending tens, hundreds of millions of dollars on trying to get a commercial facility going. It's going to be a while before they start generating revenue. And this is the most dangerous phase for a given technology. And Boston Metals it does hot electrolysis, right? So electrodes go into iron ore. Aqueous oxide electrolysis is a bit different. You put the iron ore in an acid bath, you run electricity through it, and the oxygen separates off, somewhat similar to aluminum. There's another company, Electra, and I believe Ciderwind is set up this way in Europe as well. That one, if I were betting my own money, I would be betting on that instead of the hot electrolysis. But I don't give stock advice, so please don't follow what I'm saying. Let's see, where we go. Now, I'm guessing electrolysis will be dominant eventually, but that we won't see a lot of it till the 2040s, and that's simply too late. Well, this is about iron ore supply and how do we upgrade it, and we'll talk about that. So this is about the net zero steel project. You guys might be interested in again, we started a global data set of existing steel plants over 1 megaton, provide a global energy monitor. And then we set up a simulation model. And as these came, we estimated roughly when their relining dates were, we then replace them with something else. And again, coming back to this, we simulated projections of demand for all countries globally, depending on where their per capita production was today, towards 200, 250, and 300 kilograms per capita by 2080. And you get something that looks sort of like this. Most countries are in the range of sort of 200 to 400 kilograms per capita. South Korea is way up there because they build a lot of cars and ships. Japan, China is up there as well because of its infrastructure build. Then you get Japan, and then we're down kind of in the oil and gas. The countries that structurally produce a lot of oil and gas use a lot of steel too. So the U.S. and Russia were in there as well. But the idea is everybody sort of S-curve, asymptotic S-curve evolves towards that 200, 250, 300. For the next round of net zero steel, we've done a whole lot of econometrics on GDP per capita, level of development, and what have you, to ascertain what this demand is likely to be. And we're probably going to see demand rise a bit with that project, but it's not done yet. And again, the middle case roughly corresponded to the IEA. I'm probably, we had to move in a hurry for this, and I'd probably let the IEA and its net zero scenario kind of bias me a bit. That's good. Boom, done. Yeah, so recycled production, we always put recycled production in first because it's so much more energy efficient. And as countries built it, we have built a function in the model to build up to ascertain the scrap availability by country. We used other people's scrap estimates. And with primary facilities, the first version of this, we didn't work on cost, we worked on political preference by region, but the next version we're doing right now is based on cost because we're doing trade flows as well for both steel and potentially green iron. So this was a very complicated flow diagram. You can go take a look at it, and basically we gave preference to BF-BOF if CCS was available, then HDRI, then blue hydrogen, and what have you. The interesting thing is decarbonizing steel does not change its costs as much as you might think. Okay, so these are the various technologies that we had in there. The yellow bars show what the effect of the carbon price. You see what it does to blast furnaces, rising from 450 to about 850 per ton. DRI rise without controls rises a bit. But you'll notice that the range of costs that we get for these different technologies is within kind of $100 to $150 a ton range, right? So really political preferences matters as much as cost when it comes to selecting technologies, and whether or not you have access to certain types of iron ore, really cheap electricity, CCS geology, and what have you. And these cost estimates are getting updated as well with the next project. This is a picture of just what happens to the steel fleet globally on an aggregate level. The red is the BF-BOF slowly disappearing. The yellow is recycled steel, secondary steel, with the various shades of green being the different clean tech primary technologies, and the blue on top are sites that we could not convert to any form of clean production, assuming that they would have to import either green iron or import steel. And that's what we're working on right now. And what's looking like in our initial results is that trade's going to be a whole lot more than that blue. It's actually going to be a highly efficient way of reducing steel production. But that's when you have uninhibited trade. Then we're going to have versions of it where you only do zonal trade, you only do trade with certain partners and what have you. This is what it looks like globally. And you just see the massive predominance of the Asian steel fleet there. And then with India coming on, and this is kind of important, I won't do this, sensitivities on CCS, sensitivities on life to stock turnover. This one's kind of important. Actually, you see the coal use by the steel fleet on the left in 2020 out to 2050. You see gas use bumping up a bit and then stopping, but then you see electricity use, our high and low, so we're at 28.7 exajoules, I believe, of coal dropping 1.5 to 5.7, but electricity use rises somewhere between 9.7 to 17.8 exajoules, which is a huge impact, right? And if you try to do all of this in China, like do this in China or Europe, you're going to put a real pinch on the electricity system. This is just benchmarks. They were looking for benchmarks in the report in terms of, you know, what is reasonable. If we had more time, I would talk about responsible steel benchmarks and how I feel about them, but I'm not going to. This is the Venn diagram of all the various ways we count steel GHG intensity per ton. If you're interested in this stuff, it's in the report. Now, this is the one I wanted to spend a little bit of time on. So this is global production by large producing region. You see the world in the top left there. You then go to China, you see how because we're basing demand mainly on domestic consumption, not export, China has kind of gone past its big infrastructure bill, and it's coming down from 1,000 megatons or a gigaton down to about 600-ish megatons, right? So they've got demand falling, and their scrap stock is building, and other people believe that you probably do more scrap than what we've got in there. So you get a huge, basically you get this pinch, and the remainder is clean steel versions in China. And they apparently, I was talking to somebody else, and apparently they have a very large capacity to make hydrogen just because of the solar and wind resources in Western China. India is the one. India, Nigeria, Pakistan, and Indonesia are the ones that scare me. India, you've got some scrap coming on, but you've got a huge, at least a tripling of demand in steel coming on fairly rapidly. Nigeria, that's going from 125 to a little over 350. Nigeria 0 to 60. Pakistan 5 to up to 50. Indonesia 7 up to 45. Potentially, there could be a very large amount of steel demand comes on in developing countries, and we need to be ready. Clean steel technologies that cost at a reasonable rate need to be ready for these countries once they hit their big infrastructure builds. European Union peaks out. The US goes mostly recycled. Japan is kind of past its peak. Now, again, part of this, a lot of this will change once you include trade. Like in some countries could just do this cheaper than others. What we've done here is we bias you do secondary first, and then you try to replace your primary domestically. Yeah, that's the big stuff there. I don't know, is there any questions on this one before I move on? Okay. Again, the big picture, again, where all the iron ore is, you know, we are likely to need to do a lot more trade in iron and steel products in order to make this all balance out. Yeah, we currently make primary iron and steel near coal and iron ore, move it where it's needed with DRI, you can split it. I've explained most of this already. So last slide. So first of all, decarbonization of steel is technologically possible using high TRL technology. We can do this, but literally we cannot let dirty plants be built past 2028 to 2030. That's very, very tight. You know, it's going to slip. This if early retirements might become necessary. China has a huge role to play here because of the large, very efficient BF-BOF capacity built in 1995 to 2015. It will be coming due for retrofit soon. We're going to need global innovation and commercialization programs, private and public green procurement, lead market contracting to make sure that technologies will replace the older facilities. Now, one thing, the hybrid project here completely changed the global steel conversation. We were kind of in the doldrums talking a lot about BF-BOF with CCS, maybe advanced smelting. Along comes hybrid, and suddenly everyone, oh, it is possible. And then about 10 different versions of hybrid came along, right? Like they will be different than Lulea, right? Because the iron ore resistant, but it really did change the conversation. And a lot of my other work is trying to change that conversation for cement. We need one ultra clean cement plant built. You know, people won't like it. They'll build the second and third differently. But by the time we get to 5, we will know how to build these things. And we'll know what the cost premium is. Sufficient usable scrap or usable iron ore has to be available. The amount of CapEx required is huge, but has been accomplished in the past. The rise in interest rates makes this a lot harder. Well, the 3 to 4% rise in interest rates, especially in emerging economies where they pay a minimum 4% more than we do in the OECD. And just the varied distribution of resources, scrap, carbon storage locations, renewable generation means every region has varying opportunities and different infrastructure needs. And that is that. The report's net zero steel, and any questions you have, happy to answer.
Very much, Chris. Before I hand over to the audience, I had one question. You were talking about the United States, you know, running essentially on scrap with a small amount, enough DRI to make it require quality. In Europe, there's really good evidence that we've been exporting low quality scrap, and like the generation of low quality scrap has increasing a lot in the past decades. And one of the strategy of the European steel industry is to get a hand on this scrap that are currently being exported. The problem is that the quality of the scrap is continuously going to decrease for every cycle of scrap use. My question is, by 2050, are we going to have to do the same as the Americans to give value to this low quality scrap sources, and about how much of roughly of virgin iron has to go into the EAF to give enough quality?
Yeah, and that completely depends on the scrap batch and how it's been taken care of, and specifically how much copper wiring has been allowed to remain in there. I've been trying. There's a slowly building literature on like people going and taking scrapings of steel in steel yards and going, what's the level of contamination? The really interesting thing is in most emerging economies, they sort metals by hand. And they do it much better than we do in the OECD because we use mechanical sorters, right, that are not nearly as careful in their separation. So oddly, we kind of need to go back to a semi-manual metal separation mode in order to keep the purity of the metals, right? Like it increased labor costs.
And if we do that, do you think that like virgin iron would not be required? Like improving the sorting and collecting would be enough?
I think there's always going to be we're always going to need some virgin iron. Like it's just, partly it is, you've got this scrap supply coming through. You're gonna do sort of stochastic spectrographic analysis as it comes through, but partly just to cover yourself and make sure we're probably gonna put in a little too much fresh DRI just to keep the quality where it needs to be, because at present, there is no way of getting contaminants out of metal once it's melted, getting copper out of iron.
Okay. Thank you. Are there questions about commenting?
Thank you very much for your epic presentation of the brave new world of almost excellent. I have a doubt about your estimation of the price, the electricity price.
Yeah.
Because you need, as far as I know, you need stable supply of electricity. So how much, what type of, and you were speaking about wind and solar, which are intermittent. So how have you placed in the cost of batteries or hydrogen as a which is, as you know, in Europe today, we have prices that vary by hour. I don't know if you have the same in North America. So, sorry, how have you put that into question?
Okay, that's a brilliant question. Okay, so first of all, there are already islanded solar fields being built in the US to serve electric arc furnaces. So they're batching and they're running off solar, right? Like they have their own islanded, they built their own solar field, they hook it directly into the arc furnace or wheel it, and they control their electricity and they know exactly what they're paying, which is this paying for the solar field. Now, there are parts of the world, so in South Africa, in Australia, in South America, right? Even at higher capital prices, you're getting 1.5 to 2.5 cents per kilowatt hour of electricity during the day, and it's predictable, right? What you do is you turn that into hydrogen, you build enough storage underground for several days of production to keep the furnace shaft spinning for several days. So the electricity is coming and going. The hydrogen is your sort of flexible point, and that keeps the DRI shaft running as often as possible. We did the math on this for a project at Seichen in South Africa. It's in climate policy if you want to see it, and we figured it would take. Basically, this facility could ship green iron to Saldanha Bay, put it on a boat to Gothenburg. In almost all cases, it would be cheaper than making steel anywhere in Europe because of now moving forward, right? So using these islanded facilities for time, if you can get cheap capital to build them, that becomes a much more consistent picture, right? So use islanded solar and supplemented with wind. You've got an underground hydrogen facility, you can make your green iron, then you make the choice whether to make steel and export that, or you make green iron and export that. So it's about controlling the electricity price using islanding as opposed to running off the grid price.
With the capex of all the installation and the electrolysis and so on.
They're pretty minimal compared to the electricity price is everything. Yeah, as long as you're running your electric, the interesting thing with solar is a lot less variable than we think, right? Like sun up, sun down, sun up, sun down. You can figure out what your capacity utilization factor. You know exactly when your cells are going to wear, when your electrolyzers are going to wear out, and then you turn it to hydrogen. You can keep the cost of this pretty stable. But that's not the case if you're running off grid electricity and you're paying the industrial grid price.
Yeah. Thank you very much. We have another question. Hi, very interesting presentation. I just wanted to ask you the nature or the type of reducing agent, and be it coal, syngas, hydrogen, affect the quality of the steel that's being produced. If it does affect it, how does it actually affect it? Thanks.
Typically, the reductant does not affect the steel. What matters far more to the final steel quality is the initial iron ore quality, the preparation that goes into the iron ore before it goes into the facility, and then how good your slagging is, right? So ThyssenKrupp is doing something where they're using DRI to produce solid sponge iron, but then they drop it into submerged arc smelter, and they melt the iron. They melt the iron for one very specific reason, so they can slag it really carefully. Then that liquid iron goes off to their BOF. right? So this is allowing them to control for quality while still using DRI. So this is one of the many variations that of the DRI process, the DRI to whatever steel making process that are coming along. So it's not the reduction process that affects the quality, it's what happens before and what happens after.
Excellent. And we have one last question in the chat. What is the reason behind the reduction in steel production for China, Japan, and South Korea by 2050?
Yeah, so there are three very different cases. So China built up this huge steel fleet in order to build infrastructure and buildings, right? Now the thing is, they're probably near the tip of that boom now. You know, like the real estate market's running out of steam. There's no reason to build unless you're trying to stimulate. Like often the real estate market in China is more. Like, you know how in OECD countries we wiggle the interest rate, they wiggle the real estate market to manage the economy. Now the problem is that market is kind of collapsing, so there's not a lot of that kind of steel demand. They built the subways they need, they built the high-speed rails they need. Really, like the natural demand is falling. They could keep exporting, and that is a choice. They could keep the steel plants and literally dump on world markets on unbelievably low prices and crush the rest of the global steel industry out of existence. That's not specialty steel. So that could happen, right? But what we've assumed is that they've shut those plants down for air quality reasons, not having to import stuff from Australia, that kind of thing.
And Korea?
It's exports. Again, it's exports. A huge proportion of the steel is transformed into goods in Japan and South Korea. And that I would say is the less defensive. Like I would argue what we did with China is quite defensible for those two countries. If they're going to continue to build a lot of ships, a lot of vehicles, what have you, they're going to need that excess steel.
Okay. Thank you very much, Chris.
Great.
And we'll move on to very last presentation. If you still have a bit of energy, I'd like to calm myself on the presentation, because I'm going to be talking to you about the final one, cement industry. So I'm actually working on the same type of project as Antoine was presenting. But more on the cement one. I'm gonna talk about I'm going to talk a little bit about pathways, but I'm also going to share a reflection on the transformation of value chain and business model using the French, what we've been noticing in the case of France. Just before we begin directly in those reflections, I'll need to be very clear about the cement production process, because this is very important to understand the rest of the presentation. So to make cement, basically you need raw materials that you're finding for it. You need limestone and clay that you crush and you blend it into a substance called raw meal. And you feed this raw meal into a clinker production system. So clinker is really the material that is responsible for the entire emissions of a cement plant, and roughly about 2/3 of these emissions are due to the process emissions. So this is chemically embedded, and about 1/3 is due to the use of energy, especially solid fossil fuels in Europe. Then once this clinker is made, you're going to crush it, blend it with secondary materials, and this is going to give you different qualities cement with different properties. So that's the actual value chain. This is what's actually happening on cement plant today. Now, what I want to say is that cement roadmaps, we've heard a lot about uncertainties in the chemical industry, petrochemical industry. in the cement industry, the pathway is much more clear. Cement roadmaps actually convey very similar narratives to reach net zero by 2050. So when you look at those, all these roadmaps, you realize that net zero will be reached by a combination of reduction in demand and energy efficiency. Some energy efficiency gains on the heat, the use of switch to use of biomass and alternative fuels for the decarbonization of the energy, reduction in the clinker cement ratio by using secondary materials, and a very large share of the decarbonization is going to be taken by the use of CCS, roughly about in the order of 50%. So the question that we've been asking ourselves in the context of this project that I'm working on in France is, how does this kind of vision narrative translate at a plant level? And does it mean that all the cement plants should undergo the same transformation? So actually, this is a rhetorical question. I'm going to show you what happens. So this is the project I was talking about, a sectoral transition plan for the cement industry. It's available in English, so you can go and have a look if you want. And in this work, we're basically looking at the decarbonization of the French cement industry. And we did three different scenarios. In the reference scenario, so that's kind of the middle consensus scenario that we've got with the industry. So this is roughly representing France, like very roughly. In France, we have a fleet of cement plants scattered around in the country, and in the reference scenario, what happens is all the cement plants undergo same kind of transformation. All the cement plants undergo a decrease in their production, a decrease in their average clinker to cement ratio, some decarbonization of the thermal mix with the use of biomass and alternative fuels, and some optimization technology. So the entire fleet undergoes this transformation. Then a subset of this fleet, actually, that are not to the best available techniques, which is the use of the dry process with the precalciner. This subset of plants will be upgraded to the BAT process. Another subset of cement fleets, which are actually favorably located in France, will be applied CCS. That'll represent roughly about 20% of the plants that we have in the country. So when you do that, and when you apply this scenario, you actually fail to reach decarbonization. So you're left with a fair share of unabated emissions, and that's mainly due to the CCS constraint we foresee in the case of France. So what we did is that we were rather disappointed with that first scenario. So we tried to think of another scenario, under what circumstances could you reach decarbonization in the cement industry. So in this second scenario, we call that extreme techno-push scenario. So this is a scenario where we applied a lot of technology, like we go all in, especially in CCS. We make strong assumptions of the use of CCS in the scenario. So you take your cement fleet and you divide it into two broad categories of plants. And the first category are the ones that are already favorably identified as favorably located close to the CCS, the future CCS region in France. In this scenario, we also assume we make the assumptions of a new CCS zone that will be deployed in the southeast, in the zone of Fos-sur-Mer, that is being investigated. So this, for this subset of plants that are located in this region, we upgrade them. So we do revamping of these plants, and we increase the production capacity. The problem with the French cement fleet is that there's composed of many different small plants with the small capacities. So for these plants, we increase the capacities, and we concentrate all the national clinker production as much as possible under these sites. And for the rest of the cement fleet, all these cement sites will be converted to grinding plants. So basically, they will not produce clinker anymore, but they will process it, they will grind it, and then produce cement. Or alternatively, they're going to be converting for the production of calcium clay, which is a secondary materials that we're going to need a lot in this scenario as well, or for the production of new more innovative alternative binders. And I'm going to talk about that in the rest of the presentation. And between those plants, something that we can expect is that some more logistics are going to be needed. We have some new fluxes of clinker, more additional flows of clinker transport and more material transport in this kind of scenario. So that's what happens in the scenario, and this is how it translates in terms of emissions. So, like I said, we can see a very big share of the emission reduction given to CCS, and that's due to this concentration strategy that we try to apply in the country. We also will do apply mineralization, which is it's just basically CCU on aggregate. We try to identify. We try to quantify the potential in France, and that's roughly what we could where we could get out of CCU. And we're also using some new types of alternative binders. So these are like geopolymer binders or other types. There are other types of polymers of alternative binders. So this is all quite nice and perhaps wishful thinking. You might wonder. Now I'd like to show you what's some of the early signs that we see in France of this kind of transformation and how is that happening. So this is a map of the French cement fleet as it was in 2021, I think. So like I said, all the cement plants are scattered around the country, located close to the raw materials. And these are the plants, the cement plants that were closed in the past decade between 2029 and 2020. So that's a bunch of them. And most of the plants were actually not closed and disposed of. They were actually converted to grinding plants with importing clinker. Here are some of the plants for which the closure has been recently announced in 2020, 2021. So that's 3 of them. And besides that, in parallel with that, we have some very important investments that have been announced, heavy investments, I mean, on these plants. And we're talking about the revamping of the plant, or massive calcium clay project for like flash calciners, or even CCS conversion for the one in the north. So we're talking dozens of millions, at least, of euros, if not hundreds. So what I wanted to say for this slide is that for cement companies, let's be clear, some plants are more strategic than others, right? At least in the French context. Cement and clinker production are likely going to decrease in France due to a combination of lower demand for infrastructure. So we're sort of plateauing in our demand for infrastructure, like the part of infrastructure is like reaching maturity in terms of roads and buildings. Secondly, we're witnessing material substitution measures that are being put in place and better efficiency standards in buildings, like what Chris was talking about in his presentation. And also, we can expect a reduction in the average clinker to cement ratio. So that means that essentially the clinker production at the plant will likely to decrease as well. Thus, cement companies, this is where I wanted to get at. cement companies face the choice already, like today, face the choice of which clinker lines to stop and which to invest in. And some of the key factors that I considered for investment decisions in the cement plants are almost in this very order here, presented here. The local market dynamic, because this is a very local market. Secondly, access to some locally sourced minerals and fuels like limestone, calcium clay. Some cement plants have been closed simply because the quarry was empty out of raw materials, and thirdly, the long-term access to geological storage is something that is a parameter that we see coming into the investment decision in France. I also wanted to talk to you about the new cementitious products that we have and the new alternative materials that we've been witnessing at ADEME, at the French Agency for Ecological Transition. 1, 2. There you go. So what I want to say is for a couple of years, especially since the publication of the last building environmental regulation that we have in France, there's been a real, we've witnessed a real big push of some new smaller entrants cement companies. These are these are typically like industrial startups that wish to penetrate the cement market with some innovative low carbon solution. And as ADEME, we have received many requests for public funding for these so-called low carbon solutions. And what we've seen is that we can divide those into mainly 3 broad categories of business model. The first category is the companies that will use either ground clinker or CEM1 or highly concentrated clinker cement, and they will blend it with some secondary constituents to make new cement, like whether it's slag or limestone. So basically, they will take the clinker or the cement, and they will do their own cuisine, their own recipes with that, and it will dilute the clinker. The second category that we can point out is those companies that are preparing and providing secondary constituents like calcium clay to already installed incumbent cement companies. Like especially true for calcium clay, but it's also true for gypsum, for instance. And the last one, this last category of actors that we've witnessed are those that propose new innovative binders that are not based on classic chemistry, but those that are based on industrial byproducts or other types of raw material as primary constituents, with possibly a very small fraction, as well as small share of clinker or an activator, because some of those are geopolymer cement. And this graph shows you the installed capacity that all of these new actors represent compared to the current cement consumption. So that is just to say that this emerging trend is not small in terms of capacity. Like it represents something that we think is quite important in the cement industry. So that's about 4 million tons of expected plant capacity development by 2026. All of these 3 categories of binders are taken together roughly. So if I had to summarize what I've just shown, I'm just going to give you a picture of the possible value chain configuration for a low carbon cement industry, considering everything that we've seen there. So this is a cement plant, and this is one of the lucky ones that have access to CCS. Let's assume that. So it will still make cement. It will decarbonize through mainly 2 measures: the switch to biomass and alternative fuels to to reduce the CO2 combustion part, and then secondly, it will switch to CCS to get a very low carbon plant. So basically, the production and the production of clinker is concentrated and low carbon, close to neutral clinker. And then we'll have a first subset of I say businesses and companies that will connect to these plants. These are the ones that will buy the cement, the CEM1, and will make their own recipes with blending them with slag, or fly ash, or limestone, for instance. Closely, we have those that will buy directly the clinker from the cement plant, and they will grind it, and similarly they will blend it with their own fly ash or limestone or pozzolanas, whatever. Then we have another set of emerging companies. Those are the ones that will provide some of the secondary materials that will be needed by 2050. And that's typically the case for calcium clay that are available in some quarries, in some already existing quarries. So there will be clay or other industrial byproducts. So we've seen project with gypsum waste, for instance, like this. And then the very last say business model that will be connected to this low carbon cement plant is the one that will produce the alternative, more innovative alternative binders. They use as a primary constituent either calcium clay, slag, gypsum, or limestone. They will possibly use an activator, an alkali activator, to make gel polymer cement. And sometimes some of the recipe includes a very small share, like up to 10 to 20% of clinker. So that gives you a possible picture of a low carbon cement value chain in 2050. So just some concluding remarks regarding this presentation. To me, it is clear that deep decarbonization might shuffle the configuration of the cement industry, but clinker is going to remain a very primary ingredient by 2050. Secondly, it's likely that the transformation will be heterogeneous across cement plants. So clearly, that means that cement plants will have to close. That's what it means, and it's already what we're witnessing at the moment. More intermediate transport can be expected in the future, which leads to the question of which places the light on the decarbonization of logistic chains. New cement players have emerged. We have seen the emergence of new cement players essentially because of climate and circular policy, like the building regulation RE 2020 in France. Some of these players seeks to use locally sourced materials. So basically, they are new entrants because they sit on a pile of waste that they think they could be valued into the cement industry. So that's usually how it works when they're contacting us. These industrial byproducts could be slag or clay, for instance. And they see that their pile of minerals has an opportunity to penetrate the cement market. And lastly, I haven't touched on that, but it's really important for the cement industry. It will take time for the norms and regulation to accommodate all of these new innovative binders, which could slow the development. And this is something we're already witnessing at the moment. So thank you very much for your attention, and happy to take questions.
And if there are questions, I have someone distributing the mic for me. Thanks.
Congratulations.
Oh, come on.
Question for your presentation. I have two questions. One, you already referred to now at the end. Those 4 million tons of new, let's say, cements or clinkers, are you really, they have that problem that nobody is going to risk that the building is going to fall. So the regulations will have to be very much assessed. Some of them, I believe, due to their chemical properties. But you are quite confident that they will be competitive. I know that the cement market is a little bit more localized, but anyway, it can travel a little. The other question is that you spoke there a very big importance of CCUS. I take it, but I was not sure that the product you are producing with the, let's say, the carbon, the CO2 extractions are also mineralized components for construction. Is that correct, or where are you using with profit those the CO2 that you extract?
So I'm gonna start with your last question, because that's the one I remember. No, no worries. So I use the term CCUS because overall we know that the cement industry will decarbonize through CCUS. The U is very not necessarily comfortable with the U because it assumes that the product, and if you're doing utilization, it assumes that the product that you're going to be producing, whether it's fuels or basic chemicals, are going to have long-lasting storage period of carbon, which is not an assumption I'm comfortable to make right today. So when I'm talking about the U, I'm more, like you said, I'm more referring to the mineralization of CO2 into aggregates, into old demolition aggregates, because that's a no-brainer. It really stores the carbon for a long period of time. Coming back to your first question, like the 4 million tons, I will try to put that in line. So the 4 million tons are the cumulative. If we add up all the plant capacity of individually all these projects, and roughly that represents between 10 and 15 projects that we've seen. If we add them all up, it goes up to 4 million tons. Are they competitive? Some of these actors already exist at the moment, and they're just they're looking to increase their capacity or develop like new recipes. But their challenge is I don't feel like their main issue or challenge is to be competitive. Their main challenge is to get accepted by the norms and regulation and in the building, because that's where the big war is happening in the cement industry, I feel.
That's part of the global competitiveness.
And it's part of the global competitiveness, yes. Thanks.
Thanks, Elliot. My question is regarding the energy intensity of the CCUs itself. CCS, sorry, in this case. Do you factor that in, and the CO2 that would be released because of the energy consumption, the additional energy consumption?
Yes. So I'm trying to. Yeah. So in this trajectory here, will come up. Anyway, I can answer more simply. Yes. So the technology that we use to model the capture of the carbon is actually nano-based technologies that needs a boiler to strip to the amine, release the CO2, and this boiler requires natural gas, runs on natural gas, and the CO2 emitted by this boiler is actually recirculated into the capture stream. And so when you factor it in and you consider the capture rate, which is 90 or 95%, you're left with you're still left with a small share of CO2 fugitive CO2 emissions. So yes, we factored it in, and the energy penalty is between 3 and 3.5 gigajoules per ton of CO2 captured, depends on the technology you use.
So at the end of the day, the cement industry would be, from energy point of view, they will be even more intensive than today.
Yeah,
Potentially.
yeah,
Undoubtedly also.
at least for those that will capture the CO2, for the cement plants that will capture this CO2, it is likely to be plus the switch from conventional solid fuels like coal and coke that is being used now to alternative fuels, substitution fuels like biomass or waste. This operation actually increases the average energy consumption between 5 and 10% for each megajoules of energy substituted, just because it is lower quality fuel that's been used. So from an energy standpoint, I think that it is likely that the cement industry will actually overall increase their energy consumption per ton of cement. Yeah.
Thank you.
I'll just check if someone online has asked a question. Otherwise, there's no more question. We can close up here. Thank you very much, everyone, for listening and for your questions. And yeah, safe travel back.